Okay, so Adam is back with his second talk.
All right, great. All right, thanks for your attention. So, okay, so in the second part of the talk, so what did we see in kind of the first part of the talk? What we did is we talked about the complexity theoretic foundations, really, of the boson sampling experiment. And what did we conclude with? Well, we said something like, well, you need to make some average case approximate hardness conjecture, but we don't know how to prove this. But we're able to support it by giving kind of average case exact hardness statements and worst case approximate statements, okay? And kind of what happened after Aronson and Arkhipov wrote their paper in 2010, 2011, was this kind of launched the experimental quest for supremacy. So a huge number of optical groups went out and they tried to perform the boson sampling experiment, and they made some serious progress here. So I think as of a few years ago, the largest experiment they did, though, involved something like 6 bosons, though more recently the PAN group made a substantial progress and performed boson sampling with something like 14 bosons that they could reliably get. But this is still kind of, out of the range of classical intractability. So if you were to estimate the number of bosons you need to do a boson sampling experiment that you couldn't, say, simulate on your laptop or something, you would need, let's say, 40 or 50 plus bosons. So this boson sampling experiment had really great complexity theoretic evidence for hardness, within kind of the abilities of mathematics, but it just wasn't yet experimentally feasible. So what happened in the intervening years is that there was serious progress in superconducting qubits by the Google UCSB group and many other groups around the world. So what happened was the Google UCSB group, but the problem was their architecture doesn't natively do boson sampling. Like, their architecture is just different than a linear optical framework. It could technically simulate the boson sampling experiment, but with some overheads that are just prohibitively hard when you have these really tiny machines. So what happened was that the Google UCSB group, in a paper by Boykshield et al. In 2016, they showed what they did is they defined kind of the superconducting qubit analog of boson sampling for their particular device. Okay? And so what is the analog version of boson sampling? Well, it's something called random circuit sampling. So what's the basic idea? The basic idea is you fix some architecture on qubit-based quantum circuits. Like, let's say I'm going to apply a gate here, then the gate here, then the gate here, and then measure. So these are my inputs. And the basic idea is the distribution over circuits they defined was basically to pick each gate of the circuit from IID from the Haar measure. So the Haar measure here on, this is just, quantum gates are continuous unlike classical gates. So this is just the notion of what is a truly random gate. So the task that they defined was to pick each gate of the circuit randomly. This is their distribution over circuits. And then sample from the corresponding probabilities distribution. And what they did is they conjectured that this task is classically intractable. Okay, so that's great. So now, as we saw from the framework from last time, we have this very general machine to take a hardness of sampling conjecture and turn it into a hardness of computing conjecture. So they made this exact same conjecture for the random circuit sampling experiment. It was defined exactly as it was in boson sampling. you just conjecture that it's hard to compute the output probabilities of random quantum circuits, this is the on average statement, approximately to within some amount of error. And if you, yes?
Sorry, I'm a bit lost with the problem description. So how is it parameterized in terms of circuit depths and circuit...
Yes, exactly. Yeah. So that's a great question. So it's, so actually, they actually proposed doing this for a very particular architecture. So by an architecture, I mean like, how are your qubits laid out and where are you going to apply the gates and how much depth? So they particularly proposed it for a 2D architecture. So it's like a grid of root n by root n qubits, and the depth actually order root n. That was the very concrete proposal. But you can define random circuit sampling, like this is a much more general definition. You can fill in any architecture you like into the definition. And actually many of the results I'll be talking about will be agnostic, largely agnostic about this choice of depth. Okay, that's a good question. Okay, so so it's true. So to formally define this problem, you have to pick this architecture as well. If you do this, and make this following kind of magical conjecture, then you can conclude that it's hard to approximately sample from this distribution in the average case. This is just what we saw last time. But now, so now this proposal had one thing going for it, which it did not provably have in the Boson sampling case. RCS has an additional property that's called anti-concentration, which is called anti-concentration. So what is anti-concentration? It's basically the statement that on average over the choice of C, this output probability P0C is relatively large. Like it's roughly what you would expect it to be, 1 over 2 to the n. All right, and what this means, the implication for this, is that our additive errors in the conjecture are actually multiplicative errors. So you can see this as in some sense saying that once you have some form of average case hardness, you know the errors that you're trying to incorporate are smaller than the signal you're looking for. So this is saying like the noise is small relative to the signal.
I mean, just from numerics, we're almost certain that holds for Boson sampling.
Yes, that's it. Exactly. Yeah. As Scott points out, Boson sampling, no one has been able to prove this, but the numerics very strongly support this. And similarly, when Google wrote this paper, they had numerics to justify this, but it was recently proven by Haro and Mehraban in 2019 that these circuits of 2D grid circuits of depth root n actually do anti-concentrate, extending work of Brandau, Haro, and Horodecki from a few years ago. Okay, so that's great. So what does that mean? So if we were to make a kind of chart of the different properties that your experiment could have, there's some things, let's fill in. I'm just going to kind of copy this chart here. So this is worst case approximate hardness. This is average case exact. This is average case approximate. And this is anti-concentration, which is something that makes the approximate average case conjecture a little more believable. So if we looked at the status of boson sampling, we have worst case approximate hardness, average case exact hardness. We don't know this, but we have numerical evidence. And this is the chart that's going to be open for every proposal we define. And in fact, there were more proposals than this that had this kind of picture. Like there's also a proposal called Fourier sampling, Pfefferman and Umans, that had this exact same status. Okay, but great. So now where did random circuit sampling fall in here? Well, random circuit sampling we know this, this worst case, average case hardness. So this is like the freebie. And we have this anti-concentration. Okay, as you might suspect, we don't have average case approximate hardness for here too. But RCS was missing some evidence that boson sampling had. Namely, it was missing any notion of average case exact hardness. Okay, so if you were to look at the status of RCS and compare it to boson sampling, this was what the picture was as of 2016 when they made this proposal. All right, and this is, as a complexity theorist, this felt a little bit worrisome or kind of begging some question, just because you're, in some sense, average case hardness is all about finding a distribution that you think is hard. Like this is the key to establishing, say, cryptographic hardness. And if you don't have any kind of average case exact hardness for random circuit sampling, then it's not that clear why you should be conjecturing average case approximate hardness, because you don't even know there's any average case hardness in your distribution whatsoever, right? So in fact, you might worry that somehow this distribution over random circuits has some additional structure that makes this problem actually much easier, much in the same way that when you pick distributions over 3-SAT, there's some distributions that become very easy, even though in the worst case, it's extremely hard. So yeah, so this was the status of the proposal. And moreover, if you look at this, you notice that none of the proposals had average case exact hardness and anti-concentration simultaneously. Maybe you could have worried that these could have somehow been in tension with one another, and well, because as I mentioned, that boson sampling had this kind of picture. There were other supremacy proposals that had these same properties of RCS as well. So for instance, there is an IQP proposal, an average case version of Bremner, Montanaro, and Shepard that has this exact same kind of pattern of checks in terms of where we have proofs and kind of where we're missing evidence. So so the next thing I'd like to tell you about is about some recent work, and this is my joint work with Bill Pfefferman, Chinmay Nurki, and Umesh Vazirani. And in this work, what we showed is that we filled in this box for random circuit sampling. So in particular, what we showed is we showed a form of exact average case hardness for computing average case output probabilities, P naught of C, for C drawn from this distribution. So in other words, this provided kind of strong complexity theoretic support to the random circuit sampling experiment. So it now kind of has the same level of complexity theoretic support as the boson sampling experiment. But moreover, we're able, there's a rigorous proof of this anti-concentration property. Okay, so while I'm filling in credit, this is Aaronson Archipov for something. Okay, and Aaronson Archipov also gave some of this numerical evidence as well. Okay, so you can now see that what this kind of work did is it brought RCS kind of up to the forefront of the best we can do as complexity theorists in order to justify these experiments so far. So yeah, so now the story of how you prove this is very interesting. So in the next, say, 10 or 15 minutes, I'm going to give you a proof sketch of how you actually prove this exact average case hardness result. And the proof is very interesting. You can see it is extending some very classic work of Lipton from the 90s, which Aaronson and Archipov had extended to their case. But there are a lot of twists and turns that come up along the way in order to make this work for quantum circuits, which have a very different structure than the sort of permanence that were previously argued about. So let me explain a little bit what I mean. So let's recall the definition of the permanent. So the permanent of a matrix A, let's say A is, let's start with the finite field case. The perm of a matrix A is given by the following exponential sum. You sum over all permutations in Sn, and then you consider taking the product of AI sigma of I from I equals 1 to n. So let me just write another formula for you. You know, you're probably more familiar with the determinant, which is the exact same quantity, but where you add in the sign of sigma into the sum. Now, it turns out that there's a very huge difference in the complexities of computing determinants versus permanents. So in particular, computing the permanent of A is sharp P hard. And in the worst case. And moreover, there's this classic result of Lipton, which says that it's also hard on average. Okay, and so I'm going to explain to you this Lipton proof now, just because it's, I think it's really like a proof from the book in terms of it being very elegant. And we're going to try to copy that over to the quantum circuit case, and then we'll kind of see that a lot of things go wrong, right? So let's formalize by what we mean it's hard on average. Well, what we're going to do in order to prove this is we're going to perform a worst case to average case reduction, right? So what does that mean? Like, let's say you're given some matrix A, which is possibly worst case. Let's talk about the finite field case. And you're also given the ability, like some algorithm, to compute the permanent of random matrices R with some high probability, let's just say with high probability over the choice of R, where R is a uniformly random element of FQ to the n by n. And the goal is to compute the permanent of A using this task. All right, so you can see that if we're able to prove that this goal is possible, this implies computing the permanent is hard on average, because we know that computing permanent of A in the worst case is hard. So if we're able to reduce it to the problem of computing random permanents, then we'll know that actually computing these permanents on average is also a difficult task as well. Okay, now how do we do this? Well, this proof is, it's really interesting. You know, at first glance, if you look at that formula and you look at that goal, it kind of looks hopeless, right? Because these random matrices R, whose permanents that you can compute, have nothing to do with this just worst case matrix A. So, you know, how do you even get started here, right? But the key here to proving average case hardness ends up being in trying to find some sort of structure in the problem that gives you the ability to infer worst case permanents from average case permanents. And in this case, the structure that we find, as in much of classical theoretical computer science, is a low degree polynomial structure. So the basic idea, Lipton's proof looks something like this. So I'm going to find a family of matrices. I'm going to pick a matrix R uniformly from FQ to the n by n. I'm going to define a univariate line of matrices, A of t, which is equal to our matrix A plus t times R. Okay, so let's assume that the finite field size is sufficiently large here, as you often do. All right, so what's interesting about this univariate line? Well, it has a few properties. The first is that A of 0, I should mention t is in the finite field too. So what's the first property of this line? Well, A of 0 is equal to A. All right, that's kind of the first property, okay? That's nice and simple, all right? The second property is the structure property. And this is that it turns out that the permanent of A of t is a degree n polynomial in the variable t. All right, why is that? Well, you just kind of look at the definition. If each entry of A is a univariate polynomial in t, which it is in this line, then the product of the entries here is, this is a polynomial of degree n, so the sum of polynomials of degree n is another polynomial of degree n. So this I'm going to call the polynomial property, because this is a property that gives structure to the problem. Okay, but this line actually has this univariate line actually has another property here that's maybe even a little more slick. And that is a property that I'm going to call the marginal property. The marginal property says the following thing. If you pick any t which is non-zero, then the distribution of a of t is distributed uniformly in fq to the n by n. So what is this saying? Well, you define this univariate line, and this matrix R is kind of serving as a one-time pad, right? And it's saying that if you were to look at any individual element of the line, it would just look uniformly random. But actually, if you looked at several of them at once, they wouldn't be independently uniformly random. They're each actually correlated with one another hugely. Like you can deduce R by subtracting two adjacent ones. But the marginal is there. So what this marginal property means is that, let's say that your algorithm here computes this permanent R with probability more than 1 minus epsilon. Well, if we were to just look at one of these individual A of t, this means that your algorithm actually would compute A of t with probability more than 1 minus epsilon, right? Because that's, this marginal this distribution on inputs is exactly the distribution that we know how to compute on average. Okay, so great. So how are we going to use this to perform the worst to average case reduction? Well, we're going to use a nice trick. The basic idea is we're going to pick some various values of t. Let's just pick them 1, 2, 3, up to n plus 1, and ask our average case algorithm to compute each one. The clever thing that you can do now is you can invoke a union bound. So the trick is something like this. By the union bound, remember the union bound doesn't care about correlations. The probability that you compute all of these A of I, all of these A of t correctly, this is more than 1 minus epsilon times n plus 1. Right? The reason is if you have some events, each one of them fails with probability epsilon, well, n of them fail with probability at most, any one of them fails with probability at most n times 1 minus epsilon, independent of how they're correlated with one another. Great, so what this means is if you just set epsilon such that this is more than 2/3, this means that, so let's say epsilon is 1 over poly. Then this means that by this union bound, you will actually have been able to compute all of these values correctly. You got everyone correct. And you can now probably see the end of the proof. If you call this polynomial P of t, which is the permanent of A of t, that means that, by polynomial interpolation, this actually fixes A of t. This fixes P of t. So now all you do is you compute this polynomial. So now you compute P of 0. And this is the permanent of A. All right, so this proof is, I think, really beautiful because it's kind of carefully balancing these two properties. One property is this kind of structure property and this polynomial property. Another property is this marginal property, which is saying that within this structure, you can still make things look random. There's actually kind of some intrinsic tension between these two properties. And when we try to port this over to random circuit sampling, this tension is going to come out in full force. Yeah, so I see your question. Yeah.
What happens if Q is not large?
What happens if Q is not large? That's a great question. I don't think I'm not sure off the top of my head if hardness is known. But I will mention that if Q is sufficiently large, polynomially large, there are much more sophisticated versions of this proof using list decoding and various tricks that actually say not only is permanent hard to compute with probability 1 minus poly, it's even hard to compute with probability 1 over poly. Like there's no algorithm that even gets some tiny fraction of permanence correct. Yeah, but there the large field size is critical again. So yeah.
This doesn't work for Q equals 2, right?
Right.
This doesn't work for Q is 2. Oh, yes, yeah. That's a good point. Yes, great point. Yeah, if Q equals 2, this is permanent as determinant. So Yeah, that's a good question. Do you know off the top of your head? Yeah.
But it would just be vacuous because the problem's easy.
Yeah, exactly. So,
no, it's not.
oh no, it doesn't. You need it more than t plus 1. Q needs to be more than n plus 1 for this to work. Yeah.
If you take Q equals 3, I think the exact answer is, I think always computing the permanent is known to be intractable for that case. But I think the right thing to say is if Q is 3, you just need a new idea. I don't know if anyone has published anything, but
Sure.
you need much more than what's being discussed for small values of Q.
Great. Thanks. All right, so now, great. So that's great. That's how you establish average case hardness. And Ayrton and Arkhipov extended this kind of from this finite field setting to the case of Gaussian random matrices, which is moving to the complex field. Well, in the case of random circuit sampling, we have a different problem. So let's try to port this over to RCS and see what happens. So how do we prove average case hardness for RCS? You know, we have the exact same setup. We're given some circuit C, and the ability to compute P0 of random circuits R, where R is drawn from this distribution over circuits where you pick each gate IID randomly. And our goal is to compute P naught of C. Okay, so let's start looking at where we can draw similarities with the permanent. Well, the first thing that we can note is that there is a low-degree polynomial structure hiding in quantum circuits. The polynomial structure is that this output probability P naught of C is actually a degree M polynomial in the gate entries of the circuit. So in quantum circuits have real gate entries, or complex gate entries. And if you consider those gate entries as variable, it turns out that P naught of C does have this low-degree polynomial property. This is by the Feynman path integral view of quantum circuits. Okay, great. So now, how can we make use of this? Well, okay, let's try to copy Lipton's proof. Well, what happens, all right, so let's take our worst case circuit C, and let's consider some circuit C of T, which is C plus T times a random circuit C. All right, so what's wrong here? Well, there's like a type error here, right? So the unitary group is not a linear subspace. So you can't take two quantum circuits and add them together, right? Actually, the structure here, the structure is the structure of a continuous Lie group. It's not a linear subspace as it was in permanence. Okay, so that's a little annoying. So let's see if we can work with that. Let's try to do something like this. Let's define some circuit C prime, which is we take our worst case circuit C and multiply it by our randomly chosen circuit R. And here when I write this, I mean like gate-wise multiplication. So by the Haar measure, this C prime is uniformly distributed. It's uniformly distributed in the unitary group. So this has the marginal property. But it's missing a parameter for us to vary, right? Like it's missing a T. Yes.
When you say gate-wise multiplication, do you mean composition, or like they have the same structure and then the coefficients of each gate are?
I mean, they have the same structure, so and you just multiply each gate separately. So like if I were multiplying like this circuit by this circuit, this were A and B, and I were multiplying this with C and D, then this thing would be equal to a circuit which is C times A, and a circuit which is D times B. Does that make sense? Okay, cool. Because you could also just say, just look at what happens on each individual gate and you'll have the same story. So this is kind of fun. Okay, great. So we need some way, we found the marginal property and the polynomial property separately. Now we need some way of combining them to get them at the same time. Okay, so let's try to do something uniquely quantum. And let's try to use the uniquely quantum ability that you can implement a fraction of a gate in quantum mechanics. So what do I mean by that? So let's pick a random gate R from the Haar measure. And let me define a new gate, R of theta. This will be R times a theta amount of the inverse of R. So this is e to the minus I log of R times theta, which I can might as well call it T, so that's a little more similarity.
Why not just plain e to the I log RT? Why?
Oh, sure. Yeah. Why? Yeah. So why rotate all the way and be back? Well, I just wanted to have some analogy. So I'll now define C of t to be C times this product with R of t. And now I want the property that C of 0 is, this is just a convention such that C of 0 is my worst case circuit. And zero is my favorite point, right? Yeah. Oh, actually, actually, now I've made C of 0 random. I made C of 1C. Yeah, this is just a convention. Okay, great. So what did we do? We basically took our worst case circuit, we totally scrambled it, and then we like dialed it a little bit back towards our worst case circuit. Like we just took some knob and we tuned it a little bit. And you can show that C of t for small t is distributed on the margin close in total variation distance to the Haar measure. Great. So we found our marginal property. That's great. So we're done, right? Well, no, there's actually still a problem, right? What's the problem is we did this and we lost the polynomial property, right? Why is this true? This is because e to the IHT is not a low degree polynomial in t. It's actually a polynomial of infinite degree. Okay, so we got our marginal property in our univariate path, but then we lost our polynomial property, which was the structure gluing it all together. Okay? All right, great. So let's just solve this again. So what's the obvious thing to do? Well, if you're a physicist and you see e to the IHT, the thing you have to do is take a Taylor series approximation to it. That's what everyone does. So let's take a Taylor series of e to the IHT. Let's define that. And then this, so now you regain your polynomial property. And moreover, this, because Taylor series are so good, this output probability of the truncated circuit is extremely close to the probability of the original one. But now you have this problem that you lost the marginal property again. So this is actually a very annoying technicality, but kind of what our main contribution was, is we actually showed that basically that's okay. So in the BF, in the work of, in my joint work with Bill and Chinmay and Umesh, what we showed is that this kind of result still has the same interpretation in terms of supremacy as it does in the if we had done it if we had recovered the marginal property as well. And the basic reason is something like this. Think about your average case approximate hardness conjecture. You're trying to conjecture that it's hard to get output a number P naught C kind of anywhere in some big interval. Like you're trying to say it's hard to get anywhere in the interval of 1 over 2 to the n poly of n. We want kind of, throwing a dart anywhere in this interval to be a hard problem. But what we did is by doing our truncation, we found another point right next to it that's hard. So let's call this P prime naught of C. This is what occurs after the truncation. So what we showed is that computing this point is hard, but you can clearly see this is necessary for the average case approximate hardness conjecture, because if you think the whole interval is hard, then of course, getting some particular points in the interval is hard. And moreover, if you could improve the approximation robustness of this, then it would cover the whole interval as well. So there's some sense in which if you improved our robustness results, then this would cover the whole thing.
Is this similar to what was done for Boson sampling with IID Gaussian matrices? I mean,
Oh, yes, but there's closeness and total variation distance, and we don't have that. But in case you're worried about this, let me quickly give a shout out. There was a subsequent paper of Movasog 19, which showed that by choosing a different path, you can recover both properties simultaneously. So therefore, Movasog's result then shows that actually, indeed, computing this point at the center of the interval is actually hard as well. So in case you were worried this was like a fundamental issue with the proof, then this has actually been fixed in subsequent work.
So, Adam,
Yes.
maybe, possibly I wasn't paying close enough attention at the beginning of the talk, but there's a difference between hardness of estimating probabilities and hardness of sampling. You make
Yes. That's correct. So the last time, so in the last talk, I kind of explained that there's a reduction from hardness of sampling. There's a reduction that shows if you have a sampler, then you can estimate most output probabilities. And therefore, if you conjecture estimating most output probabilities is very hard, then you get the non-existence of a sampler as well.
Yes, you can estimate most of them. Oh, I see.
Yes, on average. This is an average case statement. So then this is now trying to provide kind of justification as to why you might believe this average case statement that estimating this output probability anywhere in this window is hard. And the evidence that we're giving is, well, we at least know there's some points in this interval that are hard, but we just don't know how to extend that by our techniques. And the reason that it seems really hard to improve the robustness of this results is that what we're effectively doing in this proof is a form of like polynomial extrapolation. And polynomial extrapolation is just very ill-conditioned. So this is basically the limitation as to why it's difficult to prove robustness results in this area.
And when you do the truncation, don't you lose unitarity?
Yes, that's right. That's why you lose the marginal property, precisely. Yep. But again, this subsequent work of Movasog shows you can actually get both of these at once if you pick your path more cleverly. Okay, great. So that's essentially the status of the Google supremacy experiment if you just look at it in terms of evidence of hardness. Well, not entirely, as I'll describe shortly. But that's the status in terms of justifying it in terms of these arguments with sharp P, right? Like, we're able to recover this average case exact hardness. We still have to conjecture average case approximate hardness. But there's a lot left to do to kind of try to ask, is this approximate average case hardness conjecture too? True. So in the next part of my talk, I'm going to switch gears. With my remaining time, I'm going to tell you about the problem of verification of this experiment. And the problem of verification is quite challenging, and it involves a kind of completely different line of reasoning than we've been pursuing to try to get evidence of hardness. Okay? So what's the problem with verification? Well, as we already pointed out, we're trying to verify a sampling problem. So we want to check that the device's output probability distribution, let me call this the experimental distribution, is close in total variation distance to the ideal distribution. This is our goal. But the problem is that, if you were to do kind of naive sampling to completely characterize this experimental distribution, this would need an exponential number of samples. Moreover, it would also need an exponential amount of processing time. That's because you would, as Thomas put it in his question last talk, like you would also need to kind of compute what the ideal distribution should be with your classical computer, and that seems very challenging. So the compromise that's been made has been to try to think of this in kind of a Goldilocks regime where, okay, so what if I just gave you only polynomially many samples from a device? But instead, I still allowed you exponential post-processing time on the classical supercomputer. So this is a small number of samples. You can't actually characterize your distribution, but you are giving yourself some power. You're giving yourself a big supercomputer. And if you pick a small enough value of n, like n is like 40 or 50, maybe you can squeeze this computation onto some giant cluster and perform some sort of computation of ideal output probabilities on your device. Of course, this is something that won't scale to n equals 100 qubits or 200 qubits, but it's something that you can do with these particular finite size experiments. So what was the proposal? So the proposal was to use these samples, and this was the proposal of Boson et al. Again. Their proposal was to use this small number of samples to compute some very coarse statistical score of their output distribution. What was the score? The score was, they said what happens if you compute the cross entropy between the experiment's distribution and the ideal distribution, right? Let's recall the cross entropy is the thing, it looks just like the entropy, but the probability, one of the probabilities comes from one distribution, and the other probability comes from the other distribution. Now, the interesting point about cross entropy is you can rewrite it as an expectation value. This is an expectation value of if you draw x from the experimental distribution of the log of 1 over the ideal distribution. And it turns out that this is very helpful. So because this is an expectation value, this actually turns out that you can estimate it very efficiently with very few samples from the device. You can estimate cross entropy very well with only polynomially many samples from the device. But note that estimating it requires you still using your classical supercomputer, right? Because the way that you empirically estimate this is you just draw some samples from your device, you kind of press the button, get a few strings x. But then you have to go with your classical supercomputer and compute its ideal output probability in the circuit if you had done everything perfectly. So this actually requires a hard computation. But the fact that this converges quickly, this is actually a special property of the output distributions of these circuits. In case you're wondering what's happening here, if you look at the output probabilities of these circuits, they tend to be concentrated. They have a very particular structure called a Porter-Thomas distribution. And this means that the logs of their ideal output probabilities are on average multiplicatively bounded. And this means that the expectation of multiplicatively bounded quantities converges relatively quickly by short alternatives. Okay, so.
Isn't Google using the linear version of this?
Yes, yeah, great question. So Google ended up using a linear version of this, but actually they computed, this was their original proposal, was to use the cross entropy. So what Google actually computed, they called it the linear cross entropy or something like this. And it's the same thing, but you don't take the log. So it's just dexp did. So this is just like the inner product between the distributions, effectively.
But this version is less sensitive to big variations.
Yeah. So yeah, I'll get to that when I explain their experiment. But basically that was just so that they could get like a better confidence interval in their value for it. It turns out that it's actually if you're looking at actual concrete numbers, it was easier for them to get a bigger confidence interval to get higher confidence in their XE value instead of their CE value. But they actually compute the CE in their supplementary materials. And it's the same number. Okay. So, great. So that's the proposal of cross entropy. It's a natural question to ask, is this at all connected with the complexity theoretic evidence of hardness? Sorry, I should say maybe what their proposal was. I should have written this first. So what their actual proposal was to take their device and they wanted to achieve some cross entropy value, which is equal to the ideal value minus epsilon. So their actual proposal was basically to perform this experiment. They know what they should be getting ideally for this coarse statistical score. Like let's normalize it such that if they are outputting a uniform distribution, they get 0. And if they do something perfect, they get a 1. You can normalize it by kind of subtracting an appropriate correction factor. And what they conjectured is that if they did their experiment and they got sufficiently close to 1, then this is a demonstration of quantum supremacy because they've actually demonstrated they've done some hard computation. So it's natural to ask, kind of, to what sense does this hold? In what sense does this hold water, and to what extent, does this connect with our complexity theoretic evidence for hardness, which was all about not about the score, but was about total variation distance. Okay, so the interesting result is that it actually does rigorously connect in some regimes, but not in others. So, in particular, in this joint work with Pfefferman, Nurki, and Vazirani, what we end up showing is that under some conditions, getting a cross entropy of 1 minus epsilon implies closeness in total variation distance to some amount, which ends up being order root epsilon. And the relevant condition is that the entropy of the experimental distribution is greater than the entropy of the ideal distribution. So if you have a form of quantum noise that's kind of pumping entropy into your device, then actually if you get a really good cross entropy score, you actually have shown that you're close in total variation distance. And as an example, like if you have depolarizing noise is essentially kind of taking your qubit and replacing it with a random coin flip. So this is your qubit going to 0, 1 with 50-50 probability. Then it does satisfy this condition. But there are other types of noise that don't satisfy this condition. So, but we also proved another statement, which is also that there exist distributions of lower entropy than the ideal that fool cross entropy. In other words, they get cross entropy score of 1, but they're very far in the total variation distance metric. Now, the interesting thing is that we had to drop the entropy of the distribution in order to get this counterexample, and there actually are some sorts of noise that could decrease the entropy. Some noise could decrease the entropy. So an example of that type of noise is amplitude damping noise. I don't know if there's a proof that this happened, but maybe it's more that there's a worry that it could happen, which is basically if you take your qubit and you replace it with 0. So this is like depolarizing noise, but it has a direction. Instead of being like an unbiased type of noise, it's a biased type of noise. It's driving you towards 0. you can think of this as kind of like resetting your quantum circuit a little bit at each step back to the initial state. And the thing is, the entropy of this distribution partly comes from maintaining kind of coherence the whole way out. So you might worry that if you get reset later on, you might not end up having as much entropy in the distribution. So what's kind of the lesson here is that their supremacy claim kind of rests on two things. Like, you both need to check the score. That's kind of the obvious thing to look at. And you need to look at the noise that there was present in the device. Their device, has a very complicated noise pattern. I think it's something that's extremely hard to characterize experimentally. It probably has some depolarizing noise, some amplitude damping noise, crosstalk, all sorts of weird things going on in the device. But there's a question of, is it actually increasing the entropy of the distribution? And the annoying thing is this is not something you can check efficiently, because estimating entropy of a distribution on an exponential size domain takes exponential samples. So this is something that, I think there's a lot of interesting work to be done to try to characterize what's happening in their device. All right, great. So you've now seen the theory of verification and of hardness. Let's talk about what Google actually did. So what was Google's result? Google UCSB. We'll get a different marker since this one's fine. What they did is they performed this experiment on a 53-qubit device. This is a root thing at all. They performed this experiment on a 53-qubit device. And what was the score that they got on this cross entropy? They got a score of basically 0.002. So if you were to plot it on this kind of axis where 0 is uniform and 1 is perfect, they ended up somewhere here, right? And on the other hand, our evidence for hardness that we laboriously went through all this average case hardness arguments and stuff to get lives up here. Essentially, they got epsilon instead of 1 minus epsilon on this score. Okay, so there's a gap, right? So, somewhat obviously. And actually, what's interesting is they think that their score is exponentially decreasing if they scale their experiment up due to noise. This is just because they're not error correcting it. But let's shelve that consideration for now, and let's just ask, what evidence is there that getting score 0.002 is actually hard, right? So there's a gap. So how can you close the gap? Well, there are basically two approaches that are being floated around now. The first approach is to make a stronger noise assumption. What if you assume that the output distribution of your experiment, this density matrix, is, say, 0.002 times the ideal one, plus 0.998 times the maximally mixed state. Okay, so what is this assumption? This assumption is kind of saying that the noise that you're producing is if you ran your circuit and you had some errors or something like that, that the resulting distribution is just totally uncorrelated with the ideal distribution. This is one way of thinking of this assumption. And there's some intuition as to why this should be approximately true, because this is coming from some kind of quantum intuitions that these circuits are very chaotic or scrambling, which causes small perturbations to kind of spread out as quickly as they can in the circuit and kind of decorrelate things. But in order to directly connect the supremacy arguments, you have to assume this is true exactly. And that's probably not true as an assumption, right? This is not something that comes out exactly from any kind of reasonable noise model. But it's reasonable to think it's approximately true. Their data kind of supports this conjecture. So that's kind of one way of squaring the circle. But there's another way of squaring the circle as well. And the other way is basically to make a different form of hardness assumption. And this idea goes back to work of Aronson and Chen in 2016. The basic idea here is something like, the basic idea is basically, can we provide some evidence that just achieving the score directly is something that's computational hard? So all right, the idea is, can we directly justify, hardness of achieving a score B on this metric, where B is kind of like your bias away from the uniform distribution. Like let's call this amount B. And the interesting answer that Aronson and Chen had was basically, yes, you can do this, but only if you make kind of additional hardness assumptions. And in particular, you have to assume something. Oh, I'll move this to the center so that people can see this better. What's essentially true is that he defined a hardness assumption that's called qua, the quantum threshold assumption. And it effectively implies the hardness of achieving a score directly. There's a kind of relatively straightforward reduction between these two things, from hardness from achieving some score to violating qua. So therefore, if you're willing to kind of make this conjecture, this additional complexity conjecture, then instead of kind of running circuitously through the pH, all the way to get back to supremacy arguments, maybe you might be able to get there just directly. And since Scott is talking next, I actually don't even have to explain this to you. I can let Scott do this in his own words. I should mention that, there's also work of Aronson and Gunn recently, which extended this to the metric, 19, that extended this to the, this linear cross-entropy metric instead of the one they originally proposed. But this is kind of the status of the complexity theoretic evidence. If you want to argue for supremacy of the experiment, you have to pay the piper somewhere. You either have to make a stronger noise assumption, or you have to make a stronger hardness assumption. And I think there's a lot of interesting questions here to work out on to what extent kind of these are true, and hopefully Scott will provide some comments on this at his talk. So, all right, yeah, thanks for your time.
Questions for Adam?
So when you sort of talked about amplitude damping, is it a problem with the measurement basis? So if you just measure in different basis, can you get rid of that entropy, or?
Oh yeah, I guess so. I think this is coming from some physics of the device where the states tend to relax down to the ground state. Like their zeros and ones actually have different energies. So this is like one source of
Suppose that you want to measure in the end, random local basis.
Yeah. Oh, I see. If you measure, you're asking if you measure in a random local basis, does this turn amplitude damping into depolarization? That's a good question. Yeah.
Entropy is basis independent, right? So you're probably thinking Shannon entropy.
Oh, yes. Okay, yeah. Okay, so that's the answer, yeah. Oh, sorry. Yeah, I'll just state what Elizabeth said. She said, von Neumann entropy is basis independent. So they have different effects on von Neumann entropy, so therefore it actually is a basis independent function, unlike Shannon entropy. Yeah. That was Elizabeth's comment.
Right. So there is a gap between entropy you get from measurement and
Yeah, I see what you mean. Yeah. Okay, yeah, good. I'll think about that. Yeah, any other questions?
Well, just a very naive question as someone not in the field. I'm trying to understand what verification means here. And in subjects that I'm used to, the prover and the verifier are different entities, and the verifier is often not someone with a vested interest in the proof being true. And
Yes, exactly.
so here, my impression is that Google is the prover and the verifier.
Yes, that's correct. Google is both the prover and the verifiable. There's a certain amount of trust here, yes. But you can also, I think the way that to view this in this framework is what they're trying to achieve here is a form of non-interactive verification. So normally when, like for instance, Urmila Mahadev's recent results and co-authors have shown that it's possible to interactively verify some quantum computation, where you get to have this dialogue between asking questions of some prover you don't trust. Here, they're trying to achieve some form of verification that the task was performed directly, but in a much more ambitious setting where it's non-interactive. They literally, the prover gives you samples. Now you want to check the prover actually performed this sampling task, right? So this is a much harder task, which is why we ended up making more assumptions in order to make it feasible. Like we had to assume something about the prover, something about the device, that its noise had some certain form in order to conclude that this kind of makes sense.
Adam, I think what one should add that it would be an easy matter to have someone else generate the circuit and send it to Google.
Sure.
Do the verification, and that probably will be done. For one thing, because it's needed for my certified randomness protocol that I'll talk about later. But it's simply that hasn't been done yet.
Sure. Yeah. Thanks.
Yes.
What you mentioned is important to characterize the type of noise that we have in the system, and we can't quite do it for 53 qubits.
Of course.
But what about like 20 qubits? Do we understand if the noise increases the entropy of the distribution or not?
That's a good question. I'm not aware of that experiment having been done, but that's a great question. And Google has publicly released a lot of their data for the samples that they got for a device, even for some smaller number of qubits. So yeah, it's an interesting question to check.
So going back to non-interactive verification, would be there a way, do you know if they think or if it's possible in practice to make it more interactive? So somehow you give the circuit like some sort of random circuit and you can adaptively change it?
Sure.
To,
Yeah, that's a good question. I mean, they have some finite coherence time, but also classical computers are really fast, so maybe that could be achievable. But yeah, I don't know off the top of my head how feasible that is. But in the case of like, why can't we run Mahadev style verification? It's because we don't have enough qubits to fit keys and stuff like this. Great. Cool. Yeah. Thanks for your time.